devices and flow of information transparently is the ability of machines to make decisions on their own and to perform their tasks autonomously. When we at Volkswagen set up a new facility in Pune, like many of our fellow manufacturers, consciously chose our automation level, which was compared to Europe, a lower level of automation, and that was in order to leverage India's workforce. Since low skill employment is taking a hit in almost every sector, the auto industry may need to look at the extent of the Industry 4.0 it needs to adopt and draw a long-term roadmap for such adoption. Hence, the auto industry needs to strike a fine balance with the advent of this new technology to the requirement of our business and the society at large. However, we need to recognize that the future of automobiles and the factories that manufacture them will be empowered by digital technologies, and therefore we need to embrace Industry 4.0 in a systematic manner in our businesses. In order to do so, we need to set up dedicated digital teams within our organizations, look at technologies which are relevant for us, focus on initiatives with overall strategic goals, and start pilots that we can scale up across the organization. And finally, the most important, we need to allocate a budget for the same. Today we are pleased to have with us two well-known experts, Dr. Diltef Zuelka from Smart Factory Germany and Dr. Gurumurthy from the Indian Institute of Science, who would share their insights on this fourth industrial revolution and how this revolution would impact our business in the short and medium term. Please join me in welcoming Professor of Indian Institute of Science, Chief Executive of Society of Innovation and Development, Professor P. Gurumurthy. Thank you.
Good afternoon, and I would like to thank the organizers of this event, Sagato Sen in particular, for allowing and inviting me to be a part of this, what appears to be a very large and well-knit community, and a critical community at that. So I have chosen to title my talk as Digitalization and I4O. And the reason is that the community seems to mix the two sometimes, and I thought I will get the vocabulary straightened out first, and then tell you a little bit about what the issues are and what is being done about it and what the opportunities are. So I want to first set the stage by distinguishing between these two terms, digitization and digitalization. And that is critical because quite often we use the word digital when we actually mean digitalize and vice versa. So think of your product catalogs, right? You would have these print catalogs that you would run every year or every other year and distribute. And once the word processing capabilities and PDF came into being, you were able to now convert this document into a computer readable form so that this could be distributed very quickly, and people could just download if they wanted it or read it on the computer to search, find out things that they want, right? So that is what I would call as digitization of information. Digitalization, of course, takes that a little forward. What we mean by digitalization is to use this digitized information and the computer to basically query or manipulate or process this digitized information. So if you were to add a shopping cart to this PDF part catalog, that would be digitalization. So somebody can search through the catalog, pick an item that they want to buy, and place an order for that, right? And so digitization is only getting it into the medium of the digital world, but to process it, manipulate it using computers is what I think the goal should be, and that's digitalization. So the product lifecycle management, which is something that the vendors have coined, and vendors are very fond of three-letter acronyms. and this probably be the one and the only one that I will use in this talk. They basically were originally about digitization of information, but the goal, of course, as always, was digitalization. But the only thing they achieved was digitization, and I'm going to go through this primarily to sort of leave the thought with you that the problems that you see today are not new. These are problems that we didn't solve yesterday, so they are again coming back to haunt us, but with some additional capabilities, so hopefully we can take another shot at solving this problem. So, the original PLM practitioners were the 4 main skills that you needed to survive in a village before the Industrial Revolution. They had the design here, and connected by neurons, they had the manufacturing here, and they had the connection with the customers because they were all within a kilometer radius of them. So they knew when their product will wear out and the customer would need a new product, they'll show up at their doorstep and sell them a shoe or a new vessel or whatever it is that was required. This whole thing got broke because of the first I, not 4 but I1, which is the original industrial revolution. What that did was to decouple the people who design from the people who make. And that, in some sense led to all the disruption that had to be solved by the tools that I'm going to talk about in the next few slides. But the goal eventually is to go back here, where the design and manufacturing are as integrated by neurons in the olden days as they will be the new e-neurons, as it were, of the modern day world. Right? That's the goal. So the first 3 revolutions, I'm going to sort of merge them in one. First one, as I said, is Industrial Revolution, where the need, the power to steam, through steam, basically took away the manufacturing task closer to the sources of water, and that is how the disruption between design and manufacturing happened, right? Because all the production was now close to sources of water, and design, of course, was wherever people wanted new products to be made. The second one, of course, was due to electrical power. All that it did did not address the gap between design and manufacturing. All it did was to, in some sense, disperse manufacturing to various locations away from the water as well, because electricity now could travel longer distances than steam. And finally, of course, the third industrial revolution was the silicon-based one, where automation and electronics that was responsible for the automation came into being. Right? Now, what did all of this achieve? Right? It achieved massive digitization of individual tasks in manufacturing. Right? If you look at the slides from the top left clockwise, right, the design was highly digital. Right? There are tools available for you to create digital description of the parts you want to make. There are machine tools that are driven by digital information to produce the part you want. Right? Of course, a lot of instructions have to be given, but it is automatic thereafter. The validation of the part you make is again largely digital. You have scanners, CMM probes that will measure the part and give you data which you can then compare to see whether it is within the deviant limits or not. And finally, large scale factory floors can be simulated and created using digital models of these. So that's possible today. But the problem is that the transition between each of these tasks requires human intervention. Right? And that's always a tricky situation because it makes the data integrity go down, A, and B, the processing limitations of the human always takes toll. Institutional memory is never built because what one expert did goes away when the person retires, and the next person has to again define the bridge between 2 silos, either design and manufacturing and inspection, or anything else. A classic example was a consulting project that we did a long time back, was a failure of a product, right? And it was determined that the failure happened due to a crack starting from a hole. The design people kept saying there is no hole, so don't talk to us. But what had happened was that the machining people had introduced that hole for some location purposes, either in assembly or in machining, but they never informed the design folks about it. Right? So these kind of gaps, are coming in because of the fact that these are huge silos and not talking to each other. So what happens when digital meets the physical? So this is all, the information is in the digital world, but the first time it became possible for the digital world to meet the physical world through this new notion of what we call additive manufacturing. All of you are already familiar with it because I'm sure you would be using it in various ways, but what I want to emphasize here are two things. One, that the good thing about this technology is that it removes this transition element between design and manufacturing. So this is the closest to printing that you can get, right, with a document. So you generate a document, it doesn't matter whether it is a Word document or a PDF or an Excel sheet or whatever it is, you give the print command and out comes the physical manifestation of the document. This is the closest that you are going to get to that, right? That you create the 3D model and ship it, press a button, and you get the 3D part out. That is one nice thing about this. But the other nice thing about this is that it changes the design space that is available to the designers dramatically, right? For the first time, what this allows is that you can have integrated structures. So you don't have to have an assembly to create a gear train. The gear train can be manufactured as a single build operation, right? And this is the only process that we have today other than powder metallurgy where you can create materials, objects with different materials in different proportions, right? So this is very unique and emerging process where digital and the physical world sort of seamlessly interface. In all the other cases, machining, forming, forging, casting, there is always this element of human intervention that comes in between, right? With all the disruptions that it is responsible for. One interesting design freedom that I would like to talk about is what is known as topology optimization, right? Now, the idea is that if you want to create a L bracket, a very simple example that I have shown in the top extreme left, right? That may or may not be the optimal shape that is capable of meeting the functional requirements that the designer might have. But we go with that because it is easy to manufacture. If you truly optimize it for performance, you get a geometry that you see on the top right corner, right? Now, the reason why we never pursued this path in the past was because there is no process available for you to make that, right? You have interesting voids and porosities inside the structure that make it optimal from a function and weight perspective. From a manufacturing perspective, it is not possible. Additive manufacturing makes that possible. And so that is one of the nice things that you can do with this amalgamation of the digital and the physical. The example on the bottom shows an upright and the suspension of a vehicle where you go from the traditional design, which is shown on the extreme left, to the optimized structure on the right, which is roughly about 30% less in weight. Right? And again, the geometry becomes feasible from a manufacturing point of view because of additive manufacturing. So that's one reasonably successful example of this integration that I talked about across two digital domains. Right? It is still not fully there yet. The metal parts are still to be proven, though there is an aircraft piece in a jet engine that has been made using additive manufacturing, and it is flying. And so we hope to see more improvements as we go forward. Now, the other complexity comes in when you introduce human in the loop, right? So you have the digital world, you have the physical world, where you are processing material and forming material, and then there is the human element in the manufacturing cycle. So one of the things that humans do in the manufacturing cycle is consume CAD models, right? Your design information. Who are these people? These are your customers who go through catalogs, your engineering team which does these design reviews and look for parts from the past to reuse, your operations which is responsible for the supply chain establishment or the maintenance, repair and operations. They all consume CAD models, but they don't want to be trained in CAD, right? And so there are tools that have come that will help them do this, right? But then again, it's a silo. You take a CAD model from your favorite system, convert it into a format that these people can consume, and then they look at it, right? So what happens if you can integrate that? So this is a tool which allows you to go directly from a 3D model, right, and build an animated assembly instruction sheet, right? So the middle frame where the 3D model is shown there will show the sequence of assembly operations, and this can be played on any handheld device, primarily because the conciseness of the representation, right? So you start with the 45 MB CAD file on any vanilla CAD system, and you have only some 60 kilobytes which can be seen on your phone, Android phone, right? And but what this integration establishes is the need for greater integration, because when we did this, The part we bought from the market, so it comes with its own, instruction sheet. And the part numbers that are listed there below, they were not there in the CAD model that was given to us. And worse still, these parts in the CAD model were not referred to in the assembly instructions at all. Right? So clearly, there is a potential problem that we are talking about here. Right? If any mishap were to happen, then this mismatch would cause great, litigations and problems. Right? So, how are these problems going to be solved? So that's what I want to now touch upon in the remaining time that I have. And that's what I call a menage a trois, where the physical, the digital, and the human come together, and hopefully, harmoniously. Right? That's the expectation. So that's the industry 4.0, right? Where you take the digital world, throw in the human element in it, and the processing of the materials in the physical domain, and provide integration and autonomy. Autonomy meaning decision-making capabilities. Right. And that's I4O for you. So if I replace the original figure that I showed you about these disconnected silos, what now I4O implies is that I connect them through some kind of a knowledge representation, which will provide the necessary integration. Right? It's not feasible to go through the details of this, but I'll try and show you some examples. This was alluded to in the opening remarks of the person who introduced this session. The reason why this is possible today, right? It was in some sense always possible, but at a different cost. But today it has become worth doing this, primarily because from the technology side, right, the sensing elements have become inexpensive, and something that you can mount on various structures and devices and parts. Right? Of course, the ability to process large amounts of data has always been there, but more than that, has now the ability to sort of go from data and information to knowledge. Here, AI element, where you are able to construct knowledge pieces from pieces of data and pieces of information. From the industry side, of course, there is always these key performance indicators, safety, product quality, and traceability. This is again a very important requirement when the supply chain is becoming very diverse and dispersed. You want traceability, and this technology is capable of providing that. So a very simple example to show this. The situation is there is an operator who is doing some riveting on a sheet metal structure, but it so happens that the setting on the torque gun is wrong, right? On the riveting gun is wrong. Now, what is available today is that there is information about the part that is being assembled, because there is an RFID tag on the part, and that can be connected to the CAD model from the system. Right? The task that is being done is known, again, because you can correlate the timestamp as well as the process sheet that is there with the operator. Right? The correct settings that need to be used is where the knowledge comes in, assuming that there is a knowledge base or a rule base which says that for this kind of part, these are the kind of settings that need to be done. But what is missing is this ability to compare all of these and alert the operator that this is wrong and you need to fix this. Right? And the reason why this is not possible today is because this notion of context is still missing from this. The fact that all of these individual pieces of information that I have listed there under the bullets are happening at the same time, and therefore a corrective action or a response has to be generated is what is missing, and that is what the promise of I4O is, that it can connect these dots and provide this information. So what do we mean? And this is not something that is new, right? A lot of you would have encountered this, right? You go book a ticket to go to Madurai in this instance, come back to some other site to do your work, and pops an advertisement for a hotel in Madurai. This is not magic, nor is it an accident. Right? This is an example of context, right? Where somebody has realized that if this person has booked a ticket to Madurai, perhaps he also needs a place to stay in Madurai. Right? Now, the advertising world has been doing it for the past 6 years at least. Right? Manufacturing is 12 times larger than advertising. So we should be in a position to beat them at this game. Right? And that's essentially what we should be trying to do, is to capture context and provide corrective responses or actions. So what is context awareness? AI people will tell you that knowledge is information embellished with context, right? So you must have the ability to sort of take information which is codified and figure out that there is a context that is required, that is causing this knowledge to be applied. And this is an important AI problem, right, of identification of context, and there are people who are working on it. The mobile world seems to have done it quite well because they have some advantages, right? They are able to locate a person quite precisely because of what is there in the user's pocket, and because of all the other information that gets stored in the mobile world, a lot of the context awareness, location in particular, can be automatically generated. So if you are here near this place, okay, here is something that you might be interested in. So that kind of information can be thrown in primarily because of the context. Right? Now for manufacturing, we need to define the same thing. Right? A very simple example would be manufacturing is an amalgamation of a part, shape, material, process, and the human. Right? And so one could define context in terms of these four elements and see if we can generate connections between data about each of them and the larger, thing about what is being done at that point in time. Right? The other problem I have listed out at the end, which is ontology, and this is again peculiar whenever you have different computer systems or applications in play. Right? If you type into Google Apple, right, the first 9 of the 10 entries that you see on the first page will be about Apple, the computer maker, the phone maker. Right? If you are lucky, if you are looking for the fruit, you may have one search result from India Mart which tells you apple sellers in the capital. That again is a result of context. That over time, Google has found that not many people are searching for, Apple the fruit on Google as opposed to Apple the machine, and therefore, the results come the way they are. So that's again an example of trying to understand the meaning of the word. Apple means both the fruit and the computer, but the interpretation comes from the fact that the pattern established over time is this, and therefore that should be the response. Right? So I come back to the original example again. You had this product catalog in PDF, you had this product catalog embedded with this shopping cart, but now you can do other things. That if this person has bought a phone, which is what you see in the bottom frame, then he might need a tempered glass shield for that. He may need a plastic casing. He may need speakers. All of them, right? So that's the I4O context, right? Where you are able to take digital information, provide some actionable input either to a customer or to a user, but based on the response of the user, you can provide more engagement, which is correct, contextually correct. That's what we want to do in the manufacturing world as well. So if this is the tool, this is the sheet, then to the sheet thickness and the tool setting match. If yes, let the guy go, otherwise stop. Right? That's what we want to achieve. So what are the elements of a smart system? I already listed them in the bullets in the earlier slide. A, that it must have data, right? It must know what is happening inside the system. And that comes from the sensing elements. You know the temperature, you know the humidity, you know the torque setting, you know the vibration profile, you know all of that. That's the data awareness or the self-awareness part of the system. Second is connectivity, of course, because you want to be able to talk to other machines, right? The machine that sent this part from the first station to the next station, and everybody else is in the network. So the storage, of course, because it has to be processed not only now but at a later time as well. You want traceability, and traceability comes from the fact that you have constant access to data that is generated about a part. And lastly, of course, is this autonomy. But autonomy is about decision making. Right? There are processes, computational processes, which look at all of these and make intelligent decisions. Right? That's the last element about this. The same thing in the example of the Amazon thing, that if you bought a mobile phone, you might be interested in this, you might be interested in that, you may want to buy this. Right? If you booked a flight to Madurai, you may need all of these services. Similar thing in manufacturing as well. You want to have this autonomy which will do this. Right? So I'm not going to dwell on this. This is a little bit technical, but I want to talk a little bit about the first two, interoperability and predictive modeling. Right? And these are going to be problems for you, so I need you to be aware of this, though the technical implementation may be done by others. So what is going to happen in I4O, one of the key elements is that you're going to have machine-to-machine communications, machine-to-computer communications. Right? So it's very important that they be able to communicate. Right? And communication is not just you sending data and me receiving it. It is you sending me data and me understanding it. Right? And I go back to the Apple example again. Right? You say, you keep referring to a plant. Right? And you refer to your plant, which is the factory shop. And I think as a botanist of a plant, and we don't converse at all. It's a very contrived example, but that's the point that I want to drive home, is that it is very important that both the applications talk the same language. CAD systems have had problems over the years, primarily because of this. Right? You cannot exchange data model created in one system, push it to the other, primarily because the BOM labels are completely different. Right? And nobody is able to take the ownership of saying that what you call a pocket is what I call something else. As simple as that. So this is something that is going to be very important. Right? How to integrate resources that are created by different practitioners at different times using different vocabularies. And ontology is like a thesaurus, right? So basically it's like the users having a dictionary, so that when you say something and look in the dictionary and say, oh, this is what you mean, and I then respond to that. That's what it means. The other thing that I need you to be aware of in I4O is this whole ability to model predictively. To build models in the computer world, which keeps track of the evolution of your process, your product, your infrastructure. Right? So if your tool has been running for 8 hours, then perhaps this is the time to change the index again. Right? So that comes from having a model that runs inside the computer, which is taking all the data from the machine and figuring out that for these operating conditions, this is the life of the tool, so now is the time that you want to stop and switch. And same thing is true for more complex machinery like a machine tool, spindle getting overheated, or a power plant, or even a motor. Right? So the predictive model basically captures all the sensory data and builds not a physical model. In most cases, these are basically patterns that are established by looking at repeated models from the past. Right? So if you look at past failure data and you see that these were the settings when it failed, these were the settings when it failed, and you sort of merge all of them and come up with a strong pattern that you can then apply. That's basically what this is. It's not physics-based. Okay. So that's essentially what the elements of I4O are. I just want to talk about the Indian context a little bit, which is that, and this is probably not India-specific, it is probably true for almost all countries and all industries, that nobody is going to throw away their entire floor just because I need to add sensors and instrument my machine tools. Right? You have to make do with what you have. Right? And the promise still remains that if we can add sensory information, the ability to transmit data about these machines to this, then we can bring in the intelligence to make this machine tool better and also allow the operator to use it better. Right? What is the problem with this idea? Bosch has been doing this. They've actually got some box solutions for legacy machines that do this. The problem with this is this, that if you look at all the sensory information that you want to get to create a good predictive model about, say, a machining process, right? Metal removal, single point tool, right? Then that's the number of sensory things that you want. Right? Some of them may be less dominant, some of them may be more dominant. But if you want it to be perfect, then this is the amount of sensory information that you need. These are all the sensors that you need to mount on your machine tool. Now, if you're building a new system, perhaps some of these can be incorporated in that. If you are a big company, maybe some of these things can be done. But not for everybody who wants a legacy machine, this is not a realistic option. So if you look at the ticks against each of the sensory information that you have, you will see that most legacy machines will have a lot more reds than greens. Right? Then how do you build these predictive models if all the sensory information is missing? I can create a predictive model in the lab or in my R&D center and pass it on to you as a user. But real time, if this information is not available, what do you do with the predictive model? Right? And so that becomes one of the first two issues that we have to worry about in the I4O scenario. One, that if you create predictive models using what I call rich data, how do you apply it to scenarios where the data coming to you is not so rich? And this is not trivial because force is one of the key inputs into most predictive models, cutting forces. Right? But to measure forces, sometimes it will cost you more than the cost of some of these legacy turning machines and milling machines. Right? So then, how do we do this? Right? So you need to come up with techniques which will take away this richness of the data and still be able to use these predictive models. AI people call it transfer learning, but that's something that needs to be developed. And the second problem that is very particular to manufacturing is that it is not a social network. Right? Meaning that on a social network, you get data about events. Manufacturing, you get a lot of data, but you don't get data about many large data about events. Because failures are not large in the machining sector. Right? And so data is always sparse. Now, is this a problem? I'm missing a slide here. Anyway, I think I'll have to do without it. But the learning community will tell you. Where am I pointing this? I need to go back to the previous slide. Okay. So anyway, you remember the slide. All I wanted to say was this, that the learning community, which is the AI community, will tell you that the larger the data, the better. No, I think you went ahead. That's okay. So the learning community will tell you that the larger the data, the better your prediction and predictive abilities are. But then in manufacturing, you have a situation where you don't have large data. And so that's another problem that has to be solved before you can apply these things to manufacturing. That how to do learning when you have sparse data sets. Right. So the last few slides, I just wanted to talk a little bit about the other aspect of this whole idea of bringing manufacturing, making it sensor-driven, network-enabled I4O in general. And so this is work that we did for a small orthotic shoe manufacturer. This is a roughly 20-year-old company. They have a 50 lakh turnover. And the problem was that the rubber incoming material would be inspected by human operators. And they would miss some of these micro holes in the rubber sheets. And that's not a bad problem, except that during the processing, some of these holes become larger. And by the time the product is done and they're ready to ship out, it becomes a quality problem. And so they have to dump the whole product. And so this is a double whammy because not only have they wasted the material, but they also have wasted all the resource in actually producing a part out of that. And they have no clue about how much material they were wasting as well. So we created for them very simple inspection mechanisms using web cameras and using a regular weigh scale that is used in your Kirana stores and some design, we created a mechanism for them to monitor the scrap in various things. Yeah, so that's the one. Now we can go to the next slide. So that's basically what was done. Next slide, please. And we put that all together so that it could be run out of a mobile phone. Right? So there is an edge device, which is a small Raspberry Pi based computing environment, and that talks to the mobile phone of the supervisor. So in a bill of materials of about 40,000 rupees, this person actually can claim to be an I4O standard orthotic shoe manufacturing company. Right? And that is something that I guess both the industry and the R&D community has to be alive to, that not all I4O solutions need the full bang sensing, computing, cloud, all of that. Right? Very simple and effective solutions are also possible, and we must not lose sight of that. So final thought, right? And this is that, this whole combination of computing, sensing, and processing, right, always has this debate of whether you can use it for automating or you can use it for augmenting, right? You can eliminate a task or you can empower the person who is doing it to do a better task. And I think, our choice is very clear that we should try and use the smart elements that are coming in to empower the human labor to do better job as opposed to eliminating the human from the operation completely, right? So very simple idea would be to use sensing to de-skill the job, right? So the stick out is not being done correctly, inserting of the tool by the operator, then you can adaptively change the tool path based can be done today with all the sensing and processing you have. This person, this job doesn't have to go. You don't need a robot to get in at the same precise level. So that is something that I would like to leave you with. And okay, one shameless plug. We have from the Department of Heavy Industry 4 what they call engineering facility centers set up for smart manufacturing. IISc happens to be one of them. There are others in IIT Delhi, Pune, and CMTI. So feel free to use this if you want to explore and try out things in the smart environment. Thank you very much. Yeah.
Thank you so much, Professor B. Gurumurthy. Ladies and gentlemen, our next speaker is the founder and chairman of the executive board of the Smart Factory KL, an industry-driven research and demonstration center for smart factory technologies, which is recognized as the birthplace of the Industry 4.0 paradigm. His research has been recognized by the Borchers Medal of Honor, as well as the higher ranking badge of honor of the German Society of Engineers and the IFAC Outstanding Service Award. He has published over 200 journals and conference papers, 5 books, and numerous other technical publications. Please join me in welcoming Professor Dr. Detlef Zulki to deliver his keynote address.
Thank you very much for the kind introduction, and also thanking my colleague for the presentation on Industry 4.0 already, because I think we do not the same right now, but you gave a wonderful step into this world of Industry 4.0, and I will show a little bit more what's happened to the industry and what will go on in future. So first of all, my background, I was a professor at the university in Kaiserslautern in mechanical engineering, and I was heading the department for automation, for industrial automation. But after a couple of years at the university, I was called in a federal research center in Germany, the German Research Center for Artificial Intelligence, where I retired about 2 years ago. And this is of applied research. So the university is basic research, this one is more applied research together with industry. And then I founded the Smart Factory Initiative in 2005 actually, as a registered non-profit association, which has the responsibility of transferring these things really into industry. So this is more transfer institution. I will talk about this a little bit later. So let's talk first of all about the challenges we are facing. I think first of all everything's getting smart, and I think everyone is agreeing to this. If we look around, wherever we are, we can use our smart devices. And this is true for all people in the meantime, for all ages, in all situations and all around the world. So I think to characterize the situation, you can say information will be available anywhere, anytime, with any content, for any user, using any device and any access. So this is the situation we are facing in our daily life already today. Second, in the field of the automotive industry, the smart vehicles are really coming. Since many years already, the real values in the cars are more and more gained by electronics and software which is built in. So today we have smart manufacturing, smart farming, for example. We have a farming research center of John Deere in our town, and what they do is really smart farming. We have the same for construction machinery in the meantime, so most of these machines are already equipped with sensors and actuators and a lot of software stuff inside. And we will have the same also for the future of our transportation, of our personal transportation, in the direction of more autonomy with autonomous cars, for example. But there are still a lot of questions open. So the questions like safety, for example, of these devices, of the security, which we have, also the security of our personal information, which is stored in the systems, the usability of all these new things, and finally also the acceptance of the people. Are they willing to pay for all this finally? Do they really have a benefit, and this benefit is worth paying for it? So the world is really changing, and also if we go a little bit deeper into our products, the world is changing in our daily life as well. So when I watch my kids, for example, they don't go in the shop mostly, but they sit in front of the computer. So they are looking for the products online on the computer. And now they can personalize these products. They can choose a color, they can do anything with these products. But finally, you push the button with a mouse click. And then, unfortunately, you will not wait 6 weeks until this product has been manufactured in, I don't know, China and transported to Germany, because the customer wants to have his product tomorrow morning at the doorbell. So this brings us a complete new situation, because production and delivery of the parts can no longer be for 6 weeks, but we need perhaps just 1 day, or let's say 2 or 3 days in the beginning, but then it will soon become shorter. So all these things are really drivers to the market. Today, the market is mostly in a way that we design in one part of the world, we let it produce in another part of the world, and then we ship it to the customer wherever this customer is in the world. This was good for mass production, was very deeply cost-driven, and we had long delivery times. This will completely change, because we will go to mass customization, a more regional production to meet the delivery times, with online ordering and immediate delivery. So this is not possible with the old global market, but we will have more regional markets, because between design, production, and using these things, there must be a very short cycle of only days. And so I assume there will be a North American market, Canada, Mexico, and stuff like this. There will be a European market, and there will be an Asian market. And we will finally see that these markets will deliver those things which are needed in a very short time and very individualized. The good question is, will that lead to a new world economic structure? I think yes, and this is a wonderful topic to discuss. I will perhaps have a few words at the end of my presentation, but we should really carefully watch the effects which this change will finally have. Let's go back to the technologies. Up till now, actually, we had our systems, everything was just using cables. So the old cars, there were the sensors and actuators, for example, and there were a lot of cables being drawn back and forth, and circuit breakers and whatever else. So already a couple of years ago, we changed all this. Also in manufacturing, we have the same. So we use building blocks today, and we use more and more networks to connect these things together. So we have controllers, we have it in our cars in the meantime, but we also have it in our machine equipment in the factories, and we have bus systems sending bus messages in both directions. The next step will be that we integrate a micro web server. So this little device which you see here on the top of it has the size of 3 pieces of cubic sugar, for example. So it's really small. It's a complete PC with a web server functionality built in. So this is just one. There are numerous others available. As soon as you build such a device in your controller, this is a part of the internet. So wherever you are in the world, you can sit in an airplane over the Atlantic Ocean. You can always talk to your sensor, to your actuator in your factory, because it's connected using the internet technologies. So now we call it the cyber-physical system, and the communication is set on the paradigm of services. So we talk about service-oriented architectures. So our building blocks of the future will offer services into a network. To make it very easy, let's compare it to a Lego brick. It's just a standardized building block. We can use it to do anything with it. And very important, a Lego brick is standardized. Otherwise, it will not work. It was quite easy to standardize it as long as Lego was the only provider of these blocks. It will be much more complicated if a lot of people around the world will provide Lego bricks. So there must be a standard. So standards are really essential for the future. And these services, or these building blocks, will be identified first by a self-identification. So when built in the first time, they say, hey, I'm new and I'm this and this device. Second, the service exploration, so we can ask these building blocks, what are your services, what are you offering? And finally, the autonomous networking. So don't care about the network and integrating these blocks, just plug them in, put the cable in, or use a wireless system, and these systems are available. So having this in mind, we can use these Lego bricks as a picture for a device. And the next step, also a machine will be a Lego brick offering services. And the next step, perhaps even a complete plant will offer services. So it's again one Lego brick in the supply chain. So this is the basic idea behind this. And I said it needs a stack of standards. Fortunately, we have most of these standards already, like OPC UA, for example, is a worldwide accepted standards which we will use. On the lower levels, we have the different access standards like the RG45 100 base something cable. If you use a cable, we have the Wi-Fi standards. And now we will have also in the factories the 5G standards in future, because 5G is not only a phone network, but it's more and more data network, especially also for industrial applications. And on the upper levels, we need some language which can be understood from all partners around the world. So if we buy a robot from Japan, for example, this robot will be plugged like a building block into your network. The network must be able to directly understand what this robot from Japan offers, for example, to a machine which was built in India. So we need the same language. This is the one solution, or we need a semantic approach to make a conversion between the different languages these machines talk. So we have different choices. There are the standardization organizations very active to create such a language, so we will see whether this will work. We are not yet ready with this, but I think this is the last step we need to really bring everything into action. So then we will have a connection, we will have the middleware OPC UA, and finally we will have the perhaps semantic solutions where we can match all the different services in whatever language they are to use it into our in our network systems and in our complete production system. So our factory of the future will look like a network actually of building blocks. So it starts on the field level with the different sensors and actuators. And these may have their own operating systems or their own middleware perhaps, but then we need one middleware to connect all these blocks. This will be hopefully OPC UA, and in future there will be also public subscriber mechanisms to this, which is very necessary. On the next level, we will have the controller level or the SCADA level. We will have an enterprise exchange bus, and we can link all the elements of a factory into these network systems so that everything is connected, and we can use the data from the ERP systems, connect them with the PLM system, send the data down to our controllers, for example. And as I said already, you can sit in an airplane over the ocean, you can still talk to your system and you can still do your changes, whatever you want to do, because you are in a worldwide network in that sense. Whether this is good or bad, whether you should do it or not, this is a different question, but technically the possibility is available. And as we are connected, for sure we have access to a lot of data. So the amount of data in the world will increase tremendously. So if you see here where we are today in the middle there, we are around now a little bit more than 33 zettabytes of data, which is stored worldwide in the meantime. And this is just a very, very small part of what's waiting for us over the next decade. So over the next years, the amount of data will be enormous. So data is everywhere, and you will have data from the past and will use data for a lot of things. So just to compare it, what we have today is about 33 million human brains, the performance of these brains. But on the other side, only 73 grams of DNA. So that shows that there's no room for improvement if we go from electronics to perhaps other methods of storing data, for example. Data is mostly driven from China right now. So if you look into the details much more, so it's mostly China storing data. You you know, all these cameras around there, all this video data is stored somewhere. So they have gigantic computer centers where they store their data, for example. What do we do with this data? Data itself is useless. We have to convert it. We have to convert it, first of all, to some sort of information, and then finally to knowledge. And from this knowledge, we have to draw conclusions finally. Otherwise, it would make no sense. So first of all, we have, for example, artificial intelligence methods to draw the data and convert data from this big data into information, like pattern recognition, for example. The next step will be then learning and inferencing, and finally there should be some sort of reasoning so that we can draw a conclusion out of this data we have. Also, augmented vision will come up very quickly. We also have a lot of examples in our factory already working so that we can support, for example, the workers, the service staff in the companies much better by supplying them online the actual information they need for this specific machine. And this is especially very helpful if you have very large plants. For example, we have not far from us the BASF plant, which is a little town in the meantime with, I think, about 30,000 people working there. And if on the weekend there will be some problem with one machine, somebody in the maintenance center, which is centralized, has to go to some place he never has seen before because he never has been there. So he needs then the information in front of this machine. What is the current state of this machine? Today he has to walk back and forth and call and things like this. In future, he has perhaps just his goggles and he can just look into the machine and will see by augmented reality what is the current state of all this. So let's switch on to my next topic. That's our smart factory in Kaiserslautern. That's the KL stands for, where Industry 4.0 really evolved. So in 2004, I had the idea after visiting a smart home in Germany, why are there so many smart homes around the world but no smart factory? So it was clear, let's build a smart factory. Unfortunately for a university at that time, it was too expensive to build a factory, so I asked a lot of people from industry and they were really happy about this and said, okay, let's do it. So in 2005, we founded an association, and this association is a non-profit registered association following the German law. We have in the meantime 53 members. And in this association, 50 employees plus the other ones of the institute, so we are around a little bit more than 100 at home. And we finance by membership fees, research projects, industry projects, but also a little bit donations as well. So this is a list, a short look on the list of our members. You will see small ones, big ones. You see many international partners, unfortunately not yet from India, but from China, Korea, from the US, for example. And these partners join together, and we have working groups, and they decide what to do in these working groups. So they try to come together, learn from each other, define new products. So we have a lot of new products already over the last years, which have been discussed first in these working groups. And they finally found out, hey, there's a new thing missing, so let's bring it to the market. And then they can build it, and then they can bring it into our factory test bed and test it there for compatibility or things like this, for example. So, as I said, 2004 was the idea. In 2005, we launched officially the Smart Factory. We started at that time with 4 people in research and in transfer. The buzzword Industry 4.0 was invented in April 2011. So this was long after we did our work, and we have wrote a report for the German government at that time for the high-tech strategy, and this report was called Smart Manufacturing Enabled by Cyber-Physical Systems. And as this report should be presented on the Hanover Fair in 2011, the advisors of our Chancellor Merkel said, this is too complicated, don't you have a more simpler word? And this was the time when one of the official guys from the ministry finally said, well, let's call it Industry 4.0. So it was never really planned, it was just for this one event, call it Industry 4.0, not knowing what happened afterwards with this word, pushing all these things up. So this was a little story at the how this came to Industry 4.0. So now we have the German infrastructure, we have German official platform of the government called Platform Industry 4.0. And also I'm very happy that we have in the meantime financed by the government so-called competence centers for small and medium-sized enterprises. So especially dedicating and educating people from small and medium-sized enterprises to bring them into the new world. The big ones can do it by themselves. They have enough power and knowledge for it. But the small ones, they need support. And this is done in these Mittelstand 4.0 competence centers. We have one of the biggest ones because we were the inventors as well of this. And these centers are right now equipped with AI trainers for artificial intelligence training, also for small and medium-sized enterprises. So you see, this is government-driven. We do this with governmental support, but as soon as it comes to real industrial use of these things, we are free from government. So we do it financed by our industrial members. So all this, bringing it together, we have 15 years of experience now with the smart manufacturing. I think we still operate the biggest transfer and research center around the world for smart manufacturing. This is a look in our lab with our equipment, with our factory. So we work together, we learn together, we present together, we work on our standards, we have our networks. Now we are just setting up a 5G network together with Huawei and the German Telecom, for example. So we will use the 5G network also for machine control. And everything we have is plug and play, following this Lego brick model. So all our modules are plug and play compatible. You can put them anywhere, just plug it in. They all have the same connector, plug it in, and it runs. We call this connector, by the way, as a joke, we call it our machine USB connector because it's as simple as a USB connector. It's bigger for sure, but it really works fine. So as we have heard already, we are still moving forward. So we started a couple of years ago with smart items. So equipping or bringing the items which we have, the sensors and actuators, on the level that they can really play the role of a smart building block. Then today, actually, we are talking about smart production. So exchange formats, about interoperability, the standards. So we moved from the component level to the factory level, actually. And on the next level, we are just starting right now a project, Smart Factory 2025. We talk about autonomous production, and this will be based on AI-based planning, error detection and correction and stuff like this. So finally, that the human being is still some sort of monitoring all these systems, but most of the work will be done also by AI technologies. So let's conclude. What we have today actually is products. You can buy compatible products, at least from our German partners. A lot of this stuff is available, also plug and play compatible. We have the equivalent standards we need. We have the market pressure behind you, why you should do all this. And we also have the knowledge how to bring it into action. So this we have achieved over these last 15 years. But we still have to solve a lot. First of all, we learned about the last years that we have to push forward the education. Not so much in the universities, this is easier, but for the people really working in the factories. We have to retrain them, to requalify them, to be ready in this new age of Industry 4.0. Workforce issues as well. How do we support the workers in future much better? How do we make them much more efficient, especially when they work in these connected network environments? We still have to solve the problem of cybersecurity, which is becoming bigger and bigger, important and more important, because when everything is connected, as I said, you can sit in an airplane and control it. Anyone around the world can try the same. So we have to find measures that this is not happening. And finally, we need also a legal framework. Contracts, for example, will change because we don't concentrate on the different electrical signals which are there, but in the contracts there must be also a liability that who is responsible for what if a module fails, for example. So how do we proceed? There's also a legal working group on the German government level addressing especially the legal framework, what we have to change in laws, for example. and so forth. So, looking back a little bit, as we heard already in the presentation before, in Industry 4.0, we made a lot of mechanization at that time. So this took us about 100 years until we succeeded with that. In the next phase, Industry 2.0, in the electrification age, about 60 years, I would say, was it lasting before we went to Industry 3.0, and this was perhaps for 40 years. So it seems that the times are getting shorter. So if we talk about Industry 4.0, we don't talk about 2 years or 5 years, but we still talk about 30 years. I'm really believing in all this. So we are just in the beginning of this new age, and we should not request that we have the full solutions already today, but we still learn and we still bring these pieces together, and this will just take time. So we are facing the fourth industrial revolution era. So this is bent to technologies, as I said, but there will come many other questions like market changes, like the geopolitical changes we are right now facing, but also qualification, quite new now, the use of artificial intelligence. Everyone is crying in Germany, hey, in the next years we will have artificial intelligence everywhere. Really? We have to support the people to use it. And there will also be a lot of social changes we have to address. Finally, it will only be successful if we bring all this together. We have learned, for example, in the mechanization era, when the steam engine came up, that there was a lot of fighting of the people, of the workers in the factory. We should avoid this, and we can avoid this by really informing them and taking them with them on the way into this new era we have. So what have we learned today? Driven by the internet, the customers require individualized products delivered in days, and this means production has to come closer to the customer markets. The manufacturers of goods must be able to follow these requirements. So a more production which is not on one big place, but it's more smaller places which are closer to the customers. We have the ability of quick adaptations to market requirements. This will be essential for success. So the customer is always changing his mind, sometimes in weeks, so we have to react on this and be able to change also our production in very short time. And finally, this cannot be solved locally, but in worldwide supply chain networks. So forget that you just make your solution, let's say, in one German town, because the company and this plant in this German town is connected in a worldwide network. So finally, we have this worldwide challenges we face. Yeah, let's look into the world. If I watch the progress we made over the last 15 years, I must say, I think there are parts of the world which want to be the winners of this situation. So mostly the highly industrialized countries like the US, Europe, more and more also China, they are pushing very hard, also Japan and Korea, for example. But other parts, they seem to be more and more the losers of this game. So they are not able to follow so quickly what's happening in the rest of the world. So the big question for me will also be, finally, who will be a winner and a loser, and what to do not to become a loser. And I think this will be also a question for India to discuss these topics, not to be in the field of the losers, but be on the side of the winners, finally. So I think it's wonderful. Let me see, there was still one more, right? So we have a lot of boundary conditions. We have more protectionism right now. We have changes in political systems and pressure from political systems. For example, in China, most of these things are really pushed forward with a lot of money by the government, so by the political forces. We have the industrial forces, we have cultural forces, and we have, and I'm very happy on this, for example, the World Economic Forum or UNIDO, trying to bring all these ideas also in those parts of the world which are not the leaders in this case, but to help them not to lose the connection to the leaders. And this is very, very important, I think, because finally we will only have a peaceful world if we have welfare for all mankind. So we should look for especially for this, and keep the people on the way into the future also on track by delivering the welfare for all of them. So thank you very much, and a wonderful event still.
Thank you so much, Professor Dr. Detlef Zulki, that informative presentation. Ladies and gentlemen, I'll now request Mr. Venkatram Mamilapalle, Country CEO and Managing Director, Renault India Operations, to conclude the session with his closing remarks.
Good afternoon, ladies and gentlemen, and thank you, Dr. Zulka and Gurumurthy, for an excellent presentation, very interesting and impressive. And as Dr. Zulka said, that smart factories are critical as we moving forward in this new revolution which is coming in, and the drivers to the changing world. It's very important that we keep an eye and adapt these new changes. As Mr. Professor Gurumurthy said, digitization and digitalization, which was an excellent explanation, and product life management, we all in automotive industry, and PLM is very critical for us, and 3 industrial revolutions which we saw. The mid-18th century saw the first industrial revolution with textile, spinning and weaving industry getting into mechanization. And as it happened, it developed a lot of other sub-industries, its ecosystem, and then followed by the next one which came in 1870s with electricity coming in and IC engine inventions. We saw its own ecosystem like infrastructure, roads, highways being built, and then subsequently to the Silicon world, which is in 1950s. Now we are now moving towards Industrial Revolution number 4.0, and this has a lot of opportunities and challenges. When I say opportunities, no doubts that the industry is moving for a high productivity at a very attractive cost, value for customers, keeping customers in mind, and a demanding needs which is coming from the society to the industry. It was not like erstwhile where industry produces and gives it to the customers and it was industry's choice. Today it is customer driven, and we are all adapting to this. When I say challenges, it's very important that skill force, as the speakers mentioned, that we need to have right skill force who are trained to adapt to the new age of industries. And it is very critical as we move ahead in this direction. We also have to keep in mind the human values and equilibrium required, and also empower not just the machines but the people, because machines should not dictate the humans through augmented realities or artificial intelligence and so on. Systems are very critical for us to make sure that everything is followed in the process of manufacturing and delivering the right product to the right customers. And everything should be based on design, not by default. So as we move ahead in this, it's necessary that we adapt the new industrial revolution. If you see way back that telephone took 80 years to come into the 100 million users bracket, and similarly internet took 10 years. But as we see, now it is taking less than a year or 2 for like Instagrams and WhatsApp. And there is a book written by Klaus Schwab, and he has mentioned this, how the evolution is happening. And it's necessary that we as leaders, and as we adapt these new industrial revolution, that we educate not only our people who are working in the industry, but also the customers of its requirements, and make sure that we keep the equilibrium as a human population. And privacy of data, it also becomes very critical as we see a lot of data going into the internet, and it can be exposing a lot of other avenues for challenging environments. So we've got to see how we can protect the data privacy. In Renault, we are adapting the industrial revolution globally, and it had been we had seen few challenges, but however, it's a good progress which we are having. It's not only the industry which is looking at industry 4.0, but the products which are coming into the market are also looking for a high level of digitalization, and the customers are not just expecting mobility, they are looking beyond mobility. So we as manufacturers of automotive have to make sure that we adapt as well as deliver the right things to the right society. So with this, I conclude. Thank you for the guest speakers, and thank you to everyone, and have a great day. Thank you.
Thank you, Mr. Venkatram Mamilapalle. Ladies and gentlemen, it's time now to felicitate our guests. I'll now request Mr. Gulpratap to felicitate Professor Dr. Detlef Zulki with a memento. I now request Mr. Venkatram Mamilapalle to hand over a memento to Professor B. Gurumurthy. I request all the dignitaries to kindly assemble for a group photograph. Thank you so much, sir. On behalf of SIAM, I'd like to wholeheartedly thank you all for your presence here. Ladies and gentlemen, with that we come to the conclusion of this session, Industry 4.0. Kindly remain seated because we're just about to begin our next session, which is the CEO's panel on revival of automotive industry.